In the last video, I introduced three different forms of a torque equation that we can use in order to derive equations of motion for a rigid body. And I'm just going to write one of them here. So we have torque of a rigid body about its center of mass is equal to its mass moment of inertia, which we represent with this I here, mass moment of inertia. So of a rigid body about its center of mass times the angular acceleration of the body with respect to frame A. So conceptually, I find it easiest to understand what the mass moment of inertia is by relating it to our equation for force. So if we have, again, force is equal to mass times the acceleration of the center of mass of a body. Let's imagine here that we're going to apply a constant force onto an object. Well, as the mass of the object increases, the acceleration resulting from that force is going to decrease, right? Again, that's because our force is constant. And so you can think of mass as almost like a resistance to a force. Now, the same thing is true if you now look at our first equation here. Here we have our mass moment of inertia term, and let's imagine we have a constant torque as we did below, so torque is constant. As you increase the moment of inertia I, your acceleration, your angular acceleration, is going to decrease. And so you can think of this mass moment of inertia as resistance to a rotational force or a rotational torque, right? And so now it should be very, very clear that there's a connection between these two equations here, right? Where here we have a linear force relating that to a linear acceleration, and in the first equation here we have a rotational force or a torque, and we're relating that to rotational acceleration. And so that should give you a sense as to how this mass moment of inertia and just the regular mass term that we're very familiar with, how those two are related to one another. Now, it's also important to note that when you calculate the mass moment of inertia for a rigid body, you need to specify the axes of rotation of that rigid body. And that's because the moment of inertia is going to be different depending on the axis of rotation. And you may note here that here I have CB, right? So this is center of mass. When I write this term CB, what I'm actually, even though the center of mass is a point, what I'm actually referring to is the axis that passes through this point. So for example, if this is our center of mass here, you can think of the axis of rotation as the axis that passes through this point and sticks out of the page. Right? And this is always going to be true because we're working in 2D. Right? So really, I'm rotating this object about an axis. And so just another example, if we have, let's say this point Q, the axis that passes through this point Q that sticks out of the page, right? So now we'll have a rotation that looks like this. And the mass moment of inertia is going to be different in these two cases. In fact, it's going to be larger when it's taken about this point Q here compared to its center of mass. And that's because for a uniform rigid body, it's always true that the minimum moment of inertia is when the rotation occurs about its center of mass. And this becomes apparent when you actually look at the equation for calculating the mass moment of inertia of a rigid body. So in order to do that, so calculate that mass moment of inertia, what you first want to do is divide your rigid body into small little units. Right? So each of those is a unit with the same area. Okay? And in order to calculate the mass moment of inertia, we sum up. So for I equals 1 to n, where n is the number of segments. So this is equal to mi, so the mass of that individual segment. If this were uniform, all of those masses would be the same, times ri squared. Now what is r? R is the distance between the axis of rotation and the center of that unit. So for example, if as I've drawn here, if my center of rotation is Q, then my R for this first unit is going to be this length. For the second unit would be this length. Third would be that, and so forth, right? And draw those out individually. Now let's look at the drawing above, right? So now let's again assume we broke this down all into individual segments. Now, if we want to calculate the mass moment of inertia with respect to the center of mass, our R for, say, this unit here is as follows. And so we're calculating R as the distance between the center of mass and the center of each unit. Like that, something like that. And so we could use this equation, or you should note immediately that this is equal to integration here. So we could take this equation in its discretized form, as shown here, and write it in its continuous form using integration. So I is going to equal r squared times dm. And in the next video, I'm going to show you how to actually use this equation to calculate the mass moment of inertia for two different rigid bodies.